So with my old age, I became softer on principles, so I'm going to give my talk in English. I see a lot of disappointment in the audience, so maybe I should shift back to French. Okay, so my title is going to be a factorization the Beilinson-Kato equals 0 infinity tensor 0 infinity of Beilinson-Kato Euler system. So this is joint work with Shanwen Wang. And there is a small paper on arXiv if you are interested. So the group is going to be G, GL2. And then I have standard notation. So A is the ring of Adel. If I want to speak of finite Adel, I remove infinity. If I want to remove infinity and P, I just do this, etc. What else? So L is a field of characteristic 0. And very soon, L is going to be a finite extension of QP, in fact. And so if X is a space of function on the G of the Adels, with value in L, let's say, then there are two natural actions on it. You can act on the left, because phi of gamma minus 1x. So that will be for gamma in G of Q. And you can act on the right, phi x G. And this G is going to be in a G of the Adels. And so these two actions commute, obviously. And then I need samples of these spaces. So first, I define algebraic functions on G. So these are the functions from G of L to L, which are algebraic, meaning that they are polynomials in the matrix of the matrix, so A, B, C, D, and the determinant inverse. So they are regular functions if you view your group as an algebraic variety. So this you can decompose in irreducible representations for the two groups. So here you have action of G of Q on the left and G of L on the right. G is GL2, it's written. It's the first thing I wrote on the board. And it will not change, I think. So this you can decompose in space of irreducible representations. So it's the sum of integer k and g, where you have Wkg tensor dual. So what is Wkg dual? I mean, the normalization is such that this is going to be the symmetric power of the standard representation tensor the determinant to the minus j. And don't ask me why I choose these notations. So this is a Q representation. And when I put a L, it just means that I extend scalar to L. Okay? And here k is an integer bigger than 0. And j is an integer. So I speak English, but I am in France, so this is bigger than 0, okay? want to put this up there. Okay, so what else do I need as functional analysis spaces? So now I actually take a finite extension of QP. And so I look at the locally constant function, which are the phi from G of A to L, which are smooth for the action of G of A, so which means that there exists K inside G of Z hat, which is open. And such that kappa is to al phi is equal to phi for all kappa in K. So these are the smooth vectors for the action of G of A. And then this is inside the locally polynomial functions, which are just the locally constant functions tensor with the algebraic functions, so locally algebraic functions. And this is inside the continuous function, which is a space of phi from G of A to L, which are continuous. What? So I wanted to make this remark. So at infinity, I want it to be continuous, yes. And so yes. So the remark is that G of R just appears only through the quotient modulo the connected component of identity, because this is totally disconnected, L. And so a function has to be a constant modulo G of R plus. So G of R appears through G of R mod G of R plus. So I could have replaced everywhere G of R by this finite set, but it's more symmetrical in this way. Okay. And then I need the cohomology with compact support. So if M is a G of QP module, I want to define H1C of M to be the set of 1 cocycles on G of Q with value in M. In M, and I want them to be trivial on the Borel, so 0 on the Borel, which is just this one. Okay, I mean, this is not a normal definition, but computation tells you that this is actually correct. And so we are going to use this for M equal well, probably just LPL, well, maybe also LCL or CL, which are these spaces. So when you do this, what you get, because you had also an action on the right of a G of A, then you get modules for under G of A. Okay? No, there is no compoundary here. It's a result of a computation, this description. No, on this Borel here, this one. Okay, and where I was? Ah, yeah, so the first thing is that actually this H1C of M of CL, well, this is Emerton completed cohomology. log of the tower of all modular curves. And then there is completed with a compact support, of the tower of all modular curves. Yeah, and so because of this, there is a comparison with étale cohomology, and so it comes with an action of the absolute Galois group of Q.
Is this what then we should use H1 hat or H1 kilowatt?
I have no idea. It's H1C, according to me. Yeah, there are at least 4 versions of it, but so, well, maybe I can tell you how you, I don't know how you prove this one. If I remove the C here, and then I would have to remove this condition and put modulo co-boundary in that case, then it would be H1 hat, and this one I don't know. Okay, and so one of the first result of Emerton on this space is a computation of the locally algebraic vectors. So as I told you, there is an action of G of the GL2 of the Adels on this space. So you can look at locally algebraic vectors. So locally algebraic means that they are smooth away from P, and at P they are locally algebraic. Okay, so it tells you that H1C ZL alg is actually, so there is a natural map from H1C LP, L, into this. And what Emerton tells you that everything comes from from this space. And this space, because of the decomposition that you have over there, you can write as a direct sum over Kj of H1C with values in LC, L, tensor Wkg, tensor outside Wkgl. So here you have a smooth action. So smooth action of G of A. And here you have an action, but only through GL2 of QP. So action, so algebraic action through G of QP.
You already said it once, but so this is G of the finite Adel, so there is only plus or minus action at infinity, right?
If you want, you can see it this way, yes. Yeah, so that's what I wanted to say. So this is a space in which you can find the Galois representation attached to modular forms. And we are going to use this to construct many objects. So maybe this was the first chapter called Emerton's completed cohomology. So now there is a second chapter called Kattos Element. So I start from a representation pi, which is a smooth, irreducible representation, an absolutely irreducible representation of G of finite Adels. So I suppose that it is defined over a number field Q of pi. So Q of pi is a number field here. And so you say that it is cohomological of weight Kg. Well, if it appears in the space which is here, so you want that m of pi, which is the multiplicity hom of pi as a representation of g of a into this h1c of LC, well, Q of pi, tensor Wkg. So you want this to be non-zero, but you actually want it to be two-dimensional. It is two-dimensional. So you don't want things that come from Eisenstein series, which will be one-dimensional, for example. What?
Only for the GA finite.
GA or GA finite. GA, yes. GA finite. Yeah. And now, if L is still a finite extension of QP, you can extend the scalar to QP. So if Q of pi is inside L, then you define M etal of pi to be L tensor M of pi. So this comes with an action of Galois now. So comes with an action of Galois. So it's a two-dimensional representation of the Galois group. And so it has many properties. But one of the properties that we are going to use is that it is de Rham. And the Hodge state weights are J and J minus K minus 1. So in particular, because K is bigger than 0, these two weights are distinct, and so you have a filtration on the d de Rham of the representation. So, so you have d de Rham of this M etal of pi as a two-step filtration. So 0 inside something I call d de Rham plus inside the whole of d de Rham. And if you use comparison theorems, etc., then you find a privileged element here. So this d de Rham plus has a privileged basis. Basis, which I call iota de Rham plus, and this corresponds. So, well, it is given by the fact. So you have a representation here. So there is a theory of the new vector. So you have a privileged new vectors, new vector of pi, and so it sends the new vector to a modular form, which is primitive. So iota de Rham plus of, so the new vector I denote by v pi. So this is related to, well, it's a modular form, f pi, which is primitive of weight k plus 2. So, I mean, to actually construct this privileged basis, you need a comparison theorem between etal and the Rham cohomology. So it doesn't come for free, but it's there. And also, by Eichler-Shimura isomorphism, you also have a decomposition of m of pi when you extend the scalar to C. Tells you that when you extend the scalar to C, then you can decompose it as a sum of two space. So you have something coming from Eichler-Shimura isomorphism. There. And so in particular, if you have a gamma inside f of pi, you can decompose it in this base, and you note omega plus or minus of gamma, the coordinate in this space. Coordinates in this base. Okay. And then the theorem of Cato is the following. Theorem Cato. So there exists a unique element, zeta of pi, which belongs to the following space. So it belongs to M of pi dual, tensor something which is the Galois the Iwasawa cohomology of the Galois attached representation. So gal Q of the measures on ZP star with value in M etal of pi. Okay. So this is just Galois Iwasawa cohomology, in fact. If you use Shapiro's lemma. And so now I have to tell you what are the unicity, the assumptions that make it unique. Otherwise, it would be a little bit strong as a statement. So if you take any gamma in f of m of pi, you take some integer between r1 and k plus 1. And what do you want again? And you want a locally constant function on zp star with value in z. And you want it to satisfy that phi of minus x is equal to plus or minus 1 times minus 1, well, some sign, which I spell out, but phi of x. So for all of this set of data, then you have an equality like this. So basically, you want to compute the exponential of the integral over zp star of phi of x. Well, first I write it and then I explain what this all means. K plus g minus r z of pi gamma. Okay, so what is this thing here? So when you take this element and you pair it with gamma, you get an element here, okay? And then an element here, you can evaluate it on any continuous function on zp star. But if you evaluate it on a function which is locally constant time power like this, you're going to get a cohomology class in a finite extension of Q, a finite cyclotomic extension of QP, of Q in fact, with a twist, the twist being given by this power here. Okay, so you get a whole bunch of residue class. So, and this exponential dual is a Bloch-Cantor exponential dual. So you restrict to QP. And so this is going to be in d the RAM of the representation that you obtain with a twist. So if you divide by the right power of Fontaine's 2 pi I, which is called by T, and so the right power is k plus g minus r, this is going to land into the field 0. It's going to land into d the RAM plus. And I told you that d the RAM plus has a privileged basis, so I can write it as a multiple of this basis. And the multiple is equal to a special value of L function, so 2 pi I to the power something, I don't care. So omega plus or minus of gamma. so the period I just introduced here, L of f pi tensor phi, evaluate at integer r, and then iota Didoram plus. Okay? So it tells you it tells you something about the exponential dual of all the twists by character which are locally algebraic and for which the power is for all critical characters. There. So it's not a trivial theorem, but it's a theorem. And so, in fact, maybe I should say that, okay, this, in a remark, is that this CP star, which is here, is just the Galois group of Q of mu p infinity over Q. But you can do the same thing with the Galois group, so same with Galois group of Q of n mu p infinity mu n p infinity, sorry, over Q. And then you get an element which I call Zn of pi. And if you look at the collection of all these elements, this is what is called the Kattos Euler system. Okay. So that's one part of the data. Now the second part is going to be, so in my title I have a factorization, Z Beilinson-Kato equal 0 infinity tensor 0 infinity. So this one is closely related to Z block Kato, Beilinson-Kato, sorry. And I'm going to introduce 0 infinity now. So 0 infinity is a modular symbol. And so how is it defined? Well, it's defined very easily. So it's a functional on H1C of CL, so the Emerton's completed cohomology, which is defined in the following way. So when you pair 0 infinity to the cocycle, so you have a cocycle which I call phi gamma for gamma in G of Q, so that's a cocycle. Then what you do, you just take phi evaluated on this matrix. Okay, so you get a function on GA by definition, a continuous function on GA. And this function you evaluate at the identity element. So that's the identity element in G of A. Okay? So it's difficult to dream of easier formula. And so what do you do now? So you want to compare this element here with the element constructed by Kato. So a priori, they don't look the same at all. So first you have to push them in the same world. And for this, we are going to use p-adic local Lagrange. So we do it in this way. So our pi yeah, so from our pi, we can define some local representation, pi L, which are actually given in the following way. You just, G of QL act on the new vector that we have chosen. And then, so this gives you a representation of GQL. And what we know is that pi is actually the restricted tensor product of all these pi L's. Okay. And the local global compatibility tells you that this pi L is what you obtain by the classical Lagrange correspondence. So local Lagrange classical, let's say. When you evaluate it on the M étal of pi dual, and you restrict to the Galois group of QL. So that's local global compatibility. And so what else do you know? And also, by definition, so your pi, you assume that it is, yes, maybe I should have said that everywhere I assume that pi is actually cohomological of weight kg, and k and g have been fixed, okay? Otherwise, this makes no sense. So by definition, so of M of pi was a multiplicity. So you have an embedding of M of pi tensor, so Vp outside P. So that's the tensor product of the new vectors at all places outside P, okay? And then tensor what comes from the place at P. And the place at P is P tensor Wkg dual of L. So that's because of the decomposition we have here. So this embeds into H1c of Cl. Okay, and so you are going to be able to evaluate 0 infinity on this space. So to do that, I mean, even to go a little bit further, you have the following theorem of Emerton, which is Emerton's local global compatibility, which tells you that if you look at the topological closure of the image, so the closure of image is just M étal of pi tensor this vector and tensor what comes out of the p-adic local Lagrange correspondence. So LLP of M étal dual of P restricted to Galois of QP. Okay, so that's one of the main theorems in the big unpublished paper by Emerton that gives you the compatibility, local global compatibility in the p-adic Lagrange program. Okay, and the last piece of information that you need to know is that this p-adic local Lagrange correspondence goes through the theory of phi gamma module. So if you have a Galois representation V, there is attached to it something which is called the phi gamma modules by Fontaine. And then on this, there is something which is LLP of V or LLP of D of V. So that's what I constructed. That's the p-adic local Lagrange correspondence. But together with this comes another diagram, which is very nice. Is that attached to this, there is the Iwasawa cohomology, which is over there. So you have H1 gal QP with values in the measures on ZP star with value in V. So this corresponds to the module, a submodule of d of v, which is dv psi equal 1. So this is a result of Fontaine. And the map, which is here, so it's an isomorphism. And the map I call big exponential dual. And this was constructed by Fontaine. And it was written by Charbonnier and myself. And here, you also have an isomorphism with some piece of the dual of this representation, except that you have to take it for the Tate dual. So you take LLP of V dual of 1, take the dual, and now you take the part on which P001 acts via acts trivially. Okay, so when you do that, you get an isomorphism between this Galois cohomology group here. I mean this, yeah, so it was our type cohomology, and the dual of representation of G of Qp. Okay, and then the theorem. Yeah, so yes. And so when you do that, you so as I say, you can evaluate 0 infinity on this space. And what you prove when you do that is that you get an eigenvector for P001. Okay, so when you evaluate 0 infinity evaluated on the space over here, on this space here, is fixed by P001. Okay, and if you believe in my diagram, so this produces some element in H1 gal QP, measures, etc. And you add this also, so you get into M et al. Of pi dual, tensor this element, okay? So, well, I'm not very precise because I get always mixed up with straight twists and duals. So, anyway, so what you get two elements that live now in the same space.
I'm sorry, can you might write that formula again?
What?
That formula is quite hard to read.
Which one? This one?
Yes.
Yes, it is on purpose. so you just adjust the parameter so that it matches what you get over there, okay? And the theorem is the following. Is that, as you could say, you have that 0 infinity is equal to z of pi in the space which is over there. I mean, in the end, you get into the same space. So now you actually can compare the two elements. What? Yeah, okay. No, sorry. So if you actually want to, it's a localization at P of this one. So 0 infinity. Okay, so the proof goes as follows. So, I mean, the theorem is quite deep, but the proof is easy if you go at the right places in the literature. So, the first thing is that you compute a formula for 0 infinity evaluated on vectors of the following type. So you take Eichler-Shimura map and you tensorize with an element in the dual of Wkg, something like this. And you get a formula that spits out periods of L functions. So that's quite standard computation. The second thing is that you need a formula to actually compute. So using this isomorphism, you need to compute z of pi evaluated on this kind of thing. Okay? So you need two things. You need a description of the locally algebraic vectors, which are exactly the elements that appear in the theorem of Kato. And so for this, you need a Kirillov model for locally algebraic vectors. So you need the Kirillov model for LLP of M et al. Of pi locally algebraic vectors. So this is done in one of my papers. And you also need a formula, for mu v, where v is locally algebraic, alge, and mu is in this Iwasawa module. Well, let's say lambda tensor v. Okay, so this is also in my big paper. And anyway, so what comes out, you get a formula that involves, so formula involving this map exponential dual, to which you apply phi minus n exponential dual of mu. So that's the second thing. And the last thing you need is something that expresses you this, which is explicit reciprocity law that is in my paper with Charbonnier. Equal, so a sum over k in z of exponential dual of integral of 1 plus p to the n zp of x to the k mu. So whatever is this formula, the main point is that by construction of Kattos element, you know these elements for the twist in the range between 0 and r minus 1. And then you compare the two formula, and they coincide. That's a miracle. And so you get enough to actually prove that, to prove this thing if, so this implies a result in the case where when the restriction of the Galois representation to Galois of Qp is irreducible. So in the case M et al. Pi restricted to Gal Qp irreducible. Okay, so that's quite a direct argument. In that case, you have enough information. And then the general case, you have to prove by analytic continuation from this case. So it's quite a delicate second step. Okay, so I will never have time to factorize my system, but maybe I can actually define it. Anyway, in the end, the theorem is written in the title. One plus p to the n zp, yes. Okay, so now Beilinson-Kato Euler system. Well, I assume the opposite there. I said that if this is irreducible, then I can conclude directly. And if it is ordinary, then I have some more problem. Okay, so how do you define it? So you have a Ziegel's unit. Which depend on two parameters. So J A over N, B over N, where A, B are between 0 and -1, let's say. So these are elements, these are units on the modular curve yn, but you have to put some denominators. So I'm not giving the formula. I mean, it helps no purpose. But the point is that you have relations between these units. And these relations, you can neatly package them, saying that there exists some distribution, Z Ziegel, so which is a distribution, algebraic distribution on matrix M21 of finite adels inside the inductive limit of these things. Okay, such that when you integrate over A plus N z hat, B plus N z hat, this distribution, Z Ziegel, then what you get is almost exactly what I wrote, except that you have, sorry, A plus R minus, so there are signs and moreover, this distribution is G of A equivariant. So moreover, it is G finite ideal equivariant. So it's a little bit of a pain to have to introduce denominators. And there is, you can regularize by introducing a C, like Kato does, to get rid of these denominators. So can regularize to remove denominators. So because what you see is that if you have G alpha beta to the C square, G C alpha C beta minus 1, well, this is actually already a unit. You don't have to introduce denominator. So in everything I am going to say now, you have to use this process to actually get rid of denominators. But I'm going to pretend that you don't have to do it because it just adds extra complication in the notations. And okay. So that's the first thing you do. And then to construct this Beilinson-Kato system, what you do is the following. Okay, let me define a group. So PQ is a group of automorphism of, so you take the algebra of all modular forms whose Q expansion is in Q bar over the algebra of modular form for the group SL2Z, Q expansion in Q. And then you have an exact sequence like this, pi Q, absolute Galois group of Q. And if you also add the action of GL2 of Q on this space, then you get a bigger group. And also you get, sorry. That's not what I want to say. So here you have the profinite completion of SL2Z hat, profinite completion of the SL2Z. So this pi Q is also the pi 1 of the modular curve of level 1, but viewed as a stack. Okay, so if you view it as it's just I view it as an algebraic curve, it's only A1, so it has no P1. But if you view it as a stack, it has a big P1. And so if you look at congruent subgroup modular forms, and then you get formula sequence like this, G of Z hat. So that's for modular forms coming from congruent subgroup. And then if you add the action of GL2 of Q on everything, then you get a bigger group called B prime Q. And now the quotient is G of A infinity, sorry, 1. And for example, if you are only interested in the Galois cohomology, the completed cohomology, so GQ is value in C of GA L. Well, this is not difficult to check that this is H1 of this HL. And if you use this kind of exact sequence, then you get an action of this group or of this group. Okay, so now what you do is that you use the Kummer theory to associate to your modular units some classes in étale cohomology. And what you obtain, sorry, Z Ziegel, you obtain an element in H1 of pi Q prime with values in the algebraic distributions over the same space as over here, M21 of A infinity, with value in ZP of 1. Okay, but because they are with values in some lattice, in fact, they can be viewed also as measures on this space. So you can view them as having value in the measure on this thing with value in ZP of 1. And then you define Beilinson-Kato element as the tensor product of two of these things, minus Kummer of Z Ziegel, tensor Kummer of Z Ziegel, and this belongs to H2 now of this pi Q prime with value in measures. Now you have M21 cross M21, which is just M22, so M2 of A infinity, with values in Z of 2, ZP of 2. Okay. And so what do you do with this element? So I have only 2 minutes, so maybe I have no time to say anything. So you have a little bit too much freedom here, so you are going to fix a finite set of places, so S finite set of places. And so if you have measured on something, you can put test functions, and the test function you are going to put are going to be of this space M2 of Z hat outside S times phi, okay? So you only look at functions that depend on the places in S, and outside S you put the function of that, and so you get in this way a Z block Kato S, Beilinson-Kato S, which belongs to H2 of a subgroup pi prime QS, where you only put GL2 of 1 over S of the measures on G of QS, which is just the product of G of QL for L in S, in ZP of 2. And this by Hochschild-Serre is the same thing as H1 of gal Q. Real value is H1 of G of Z 1 over S. And then the measures on G of QS. The measures on G of QS with value in ZP of 2. And this space here is just the dual of completed cohomology. So it's a dual of completed cohomology with compact support. With compact support of the tower of modular curve curves of level dividing S, of level dividing, for which all the prime appearing in the level are in S. Level S infinity. Okay, so you get an element in here. Yeah. And okay, and so you have H1 of Galois inside this big cohomology, which is, in fact, it's not the dual, it's a Tate dual. Tate dual, okay? And so now you use Emerton's factorization. Factorization of completed cohomology. So this big thing you are going to write as a tensor product of a big representation of GL2 of QP times two-dimensional Galois representation, okay? And yeah, so you have, so you're going to evaluate this ZBK S on this tensor product, and one of these elements is going to give you 0 infinity, and you are going to compare what you get with a tensor product of 2 0 infinity over there. So one of the 0 infinity over there is really going to be a 0 infinity, meaning a dual of this representation of GL2 of QP. And the other one is going to come from reinterpreting the Galois cohomology, which is here, as Iwasawa module, and using a periodic local Lagrange, okay? And then, so you want to prove a formula like this, and then on the left, you are going to use test functions. On the left, you use Kattos computation, and you are going to get, using Rankin-Selberg, a product of of values of two L functions. And on the right, as we saw here, each 0 infinity gives you one special value of L functions. And so in the end, what you get is some kind of algebraic version of Rankin-Selberg method. And I stop here. I'm already 2 minutes beyond.